Muted.
So welcome everyone. Thank you for attending our webinar 2. For those who attended webinar 1, welcome back. For those who haven't, you are welcome to check our website and download our webinar 1 presentation, if you please. And just a few announcements before we start. One, I'd like to make sure that everybody's muted so we don't have external sounds interfering with the presentation. You will be able to type in your questions here on the chat box, and we'll address them by the end of our presentation. Secondly, this presentation is being recorded, and all the material regarding the recording and any copy of the PDF will be made available to you tomorrow, along with a feedback survey that we request you to fill it out, not only for our own feedback, but especially for those who are interested in receiving a sample heat exchanger. You need to put in your request there in that feedback survey. So we encourage everybody to do so. So again, this is our second webinar on a series of small diameter copper tube fin heat exchangers that OTS and ICA have partnered up to work with. And on webinar 2, we have Burr Oak and Heat Transfer Technologies as well. So here are the 4 partners working on this particular webinar. Burr Oak and Heat Transfer Technologies are the experts on the subject matter, so they will they prepare most of the material, and we'll go over the presentation for you. And today's speakers include me, Daniel. I'm an engineering manager at the Optimized Thermal Systems. I presented webinar 1, and today I'm only going to give an introduction to our webinar 2. But I have here my colleagues Rocky Smith, product manager at Burr Oak Tool, and Joran Shabtai, president of Heat Transfer Technologies. So this presentation, as I mentioned before, is on the construction of small diameter copper tube fin heat exchangers. I'm going to talk about the manufacturing process, historical trends, and the challenges and solutions that these guys have been working really hard to come up with solutions for it. And just for you to have an idea of the context of this thing, we're talking about millions of heat exchangers being produced every year, multiple heat exchangers per second being constructed. So the contents of this presentation have a huge importance in the whole heat exchanger industry. So let's start with a brief introduction. I believe that most of you are familiar with the concepts of round tube plate fin coils. On this slide, we're showing a few examples here on the top. And the reason why we use round tube plate fin coils in HVAC applications, we have very well-established technologies, the state-of-the-art, has good water shedding properties, and most importantly, we have higher flexibility in terms of customizing fins and tube and coil geometry that allows exploring a wide range of new concepts. So what are the main parts of our tube fin heat exchanger? This coil is showing the anatomy. This slide is showing the anatomy of our coil. Here on the left hand side, we have a representation of a coil with the straight tubes going in this direction, and the fins, they are placed transversely to the tubes and stacked in this direction. So the main parts that we have is the hairpin, which is a bent tube that inserted into the stack of fins, and they are connected on the other end by the return bands. In between the hairpin band and the return bands and the fins, we actually have the end sheets, and we have the actual fins, probably the most complex part of our heat exchanger. And here are the nomenclature of the main parts of our fins. We have the collar, pointed out here, which establishes the distance between one fin and the other. We have the edge form, the collar base, and the fin enhancement. We have different fin enhancements, possible fin enhancements, and usually we have them in between the tubes, and will be discussed further on in this presentation. Now, when we talked about flexibility, in terms of overall geometry of the coil, when they are manufactured, we'll call it a flat coil, where the tubes are straight and similar to what we saw in the previous slide. But given some of the design requirements in terms of space allocation, we can actually conform these coils into different shapes. So once they're produced, we have the straight tubes, and then we can bend them so that they will have new forms such as L shape or U shape and so on. And as an example, for those who are familiar with the outdoor coil or condenser outside our houses, it's an example of a formed or composite coil that we have on our daily lives. Okay, so this was just a brief introduction. I will hand the presentation over to my colleague Rocky, and he's going to talk about the coil manufacturing in detail. Thank you. Go ahead.
Okay, thank you, Daniel. In this portion of the presentation, we will outline the general coil manufacturing process. This is a general flow chart of the manufacturing process for creating round tube plate fin coils. On the left are the raw materials or inputs into the coil assembly process. These are fins, tubes, end plates, and return bends. These raw materials are brought together as the coil assembly process begins with the lacing process, and then progresses to the expansion process and then the brazing process, where the coils meet up with the return bends. While the brazing process may be the final step in assembly for most coils, some coils, like composite coils, will undergo an additional step to form the coil into particular shapes for installation into housing. We will analyze the processes in more detail by starting with the fin manufacturing process. Fins may be of two general styles of patterns, inline or staggered. In either case, the hole spacing is defined as the distance between holes in the direction of the feed. Fin width is defined as the distance between holes perpendicular to the direction of the feed. The die progression determines how many rows of holes are produced for every stroke of the press. In this example, this is a 4-progression die, meaning that for every stroke of the press, 1 feed stroke of the die will occur, but 4 full rows of holes will be produced across the entire width of the die. Slit positions determine the final row widths of the fins being produced. Most dies can be adjusted to provide any multiple of fin widths to be produced. As we discussed during the introduction, round tube plate fin constructed coils are highly customizable. As such, there are many options available to the design of fins. This allows designers to tailor the fin, for instance, to alter the flow of air across the fins and maximize the heat transfer capabilities. You can see in the picture below many of the examples of fins that can be produced. There are 4 primary fin forms for the fin surfaces, okay? These 4 here: plain surface, V-waffle, sine wave, and modified sine wave. The direction of flow through the coil is from the left to right. In between the holes, we have what we call enhancements. There are 2 primary enhancements that we deal with. One is called the lance. I believe in the first webinar this was referred to as a slit feature. The other is a louver. Lances are features that pierce and raise the material from the formed surface. Louvers are features that are pierced and twisted on the formed surface. There are considerations for using one type versus another. For one example, in agricultural applications, it may not be desirable to have a louver type enhancement due to materials in the atmosphere around such equipment that would cause clogging of the fins. 2 common features on fin designs are the rippled edge feature and the raised collar base. A rippled edge is used to increase the leading and trailing edges of the fin surface. This also helps to reduce fin damage during handling of the coils before and after expansion. Raised collar bases are used to improve the lacing operation by nesting fins. The flare at the top of the collar is contained by the pocket provided by the adjacent fin to limit misalignment between fins. Another area of customization within a coil is the fin density. We refer to this as the fins per inch. The fins per inch of a coil can be altered to customize the surface area versus pressure drop across the fin. Most fin dies will be capable of a particular range of fins per inch based on the material being used. This diagram shows a typical die and line layout. Fin stock is brought in from the rear of the line of the rear of the press. As the press operates, the fin stock is fed through the die to produce the fin. At the front of the line, the suction unit and the stacking unit are used to contain and collect the finished fins. This is an example of a progressive ribbon stamping die. The upper half here is separated for clarity. The upper and lower halves of the die set work in concert with one another to create the fin. In this picture, the feed direction is from the back to the front. Draw stations produce the collars by progressively drawing and shaping the fin stock. The final draw station creates the fin surface. Pierce station punches the hole through the material to create the collar inner diameter and collar base. Enhance station creates the louver and or lances of the fin surface. The re-flare station creates the flare portion at the top of the collar, establishes the collar height and flare diameter. The edge trim station trims the overall stock width down to the appropriate width. Slit stations cut the material parallel with the feed direction to create the rows required for the fin. The feed station is the station that pulls the ribbon through the die on the strokes of the press. The final station is the cutoff station, which cuts the material perpendicular to the feed direction to create the overall fin length required. Here we have a video of the press in operation. You can see the upper half of the die here stroking up and down with the press. So every time it's doing this operation, it is forming all those stations at one go as the fin is being progressed through. This is the feed portion of the die. You can see the fin stock here being pulled through at every stroke. At the top of every stroke, the fin die is moving the feed forward. Here we show the suction unit up here at the top of the video, and then the stacking unit at the bottom. You can see the fins as they're being produced are guided out from the die. We call this a suction sheet up here. A vacuum holds the fin streams up against the suction sheet as the die is completing the process of the full length of the fin. The suction sheet keeps it aligned with the stacking unit below. Once the die performs a cutoff stroke that you see here, the vacuum pressure is released and the fin drops down to the stacker unit. The stacker unit is a series of vertical rods aligned with the fin holes. As the fin drops, the rods contain and guide the fin until reaching the stack below. Next, we will discuss how the tubes and return bends are produced for the coil assembly. For the next portion of the presentation, I would like to hand it over to my colleague, Yoram.
Hi, I'm going to describe the tube forming. There are two methods for producing inner grooved tubes. As a recap, I'd like to mention that inner grooving is performed to dramatically enhance the tube heat transfer. There are two methods, as I mentioned. The first one we're going to cover is the roll and weld method shown here. And that method starts with a copper strip. Various inner groove patterns are produced using an embossing process as shown on the top. In the middle, you can see an example of one form of embossing. After the embossing, the strip is folded round and welded either by a gas tungsten arc weld, shown in the middle section, or by a high-frequency weld process, shown on the bottom section, each with its advantages and parameters shown on the right. The next process is a cast and roll. This method starts from the copper melt shown on the top left. Large diameter tubes are extruded from the melt, and a floating mandrel inside the tube produces the grooves, as shown in the middle of the slide. Both methods reduce initial tube diameter to smaller sizes by a drawing process. The tubes are then coiled, annealed, and packed, as shown on the bottom right. Interestingly, one 100 kilogram cast billet will produce 3,000 meters of 5 millimeter OD tube. This equals to 220 pounds will produce 1.9 miles of 5 millimeter tubing. Back to you, Rocky.
Thank you, Yoram. Now that we have the tubing created, now let's talk about how we will construct the particular tubes we will use for the construction of our coils. There are two basic styles of coil assemblies that we typically deal with. One is a hairpin constructed coil, another is a straight tube constructed coil. The preferred method is to use the hairpin tubes because there are half as many brazing connection points versus a straight tube constructed coil. To produce hairpins, the vertical bend hairpin bender is used. This machine can develop hairpins up to 4 meters in formed length. It processes multiple hairpins per cycle. The tubing is brought in from the rear of the machine in the coiled stock through the uncoiler system. Finished parts are bundled and stored in bins or carts. For coils requiring longer than 4 meters in length of tubing, the straight tube construction is the solution. To produce straight tubes, the straight tube cutoff machine is used. Here, a single tube is formed per cycle. Also, just like the hairpin bender, coiled tubing stock is fed from the rear of the machine, but alternatively, you can have a straight tube bar feeder system. Typically, the cutoff machine would perform an end forming operation at one end. This reduces the number of tube ends to be formed during the expansion process. To create the return bends required for the coil manufacturing process, there is a suite of machines to use together. The return bender accepts coil-fed tubing from the rear of the machine and bends and cuts the tubing to create the U-shaped bends. Once this is completed, the bends are transferred to the return bend cleaning unit. This machine cleans and deburrs the return bends using solution and solid media in a vibratory bowl. Once the bends are cleaned and deburred, the bends are dried before leaving this machine. Once they are done, they are transferred to size and ring machine. Here, the size and ring machine precisely sizes the dimensions of the legs of the return bends and applies a brazing ring. All three of these machines can be assembled together into a single return bend production line by adding conveyors to move the bends from one machine to another. Now that all the components have been made for the coil, we are ready to assemble the coil. The first step in the assembly process is lacing. Here we bring the fins, tubes, and end plates together to assemble the coil before the expansion process. The typical lacing process involves removing fin stacks from carts that have been staged and aligning them on a lacing table. Typically, for longer coils, that would require multiple fin stacks from the cart to be assembled together to complete the entire length of the coil. Hairpins or straight tubes are pulled from bins or carts, and lower end sheets are installed, and the tubes are inserted into the fin stack and through the end plate as well. Tubes are supported by the operator, but sometimes the operators must twist, turn, and wiggle the tube to move the tube through the fin stacks. There are automated lacing machines available for this operation. However, they are primarily suited for shorter coils. Once we have completely laced coils, they are used immediately or staged for expansion. Coils may require multiple operators to handle them depending on the length and shape of the coils to prevent sagging or bowing of the coil along the length. The next step in our manufacturing process is the coil expansion process. This process is usually performed by a mechanical expander. The expansion process creates a rigid coil from loose raw material by expanding the tubing out from the inside to contact the collars of the fin. In the case of a mechanical expander, this is accomplished by driving steel balls through the tubing. These steel balls are attached to rods that are driven by cylinders or screws. As the bullets enter the tubing, the bullets expand the tubing to create physical bond between the tube OD and the fin collar ID. As the tube is expanded, the tube length is shortened if it is unrestricted. At the end of the cycle, the expander creates an end form on all the tubes required to mate with return bends. Here you see the before and after states of the coils, tube ends. These machines can be oriented horizontally or vertically depending on requirements. All the tubes may be expanded in one cycle or progressively depending on production volume requirements. Coils also may be loaded horizontally or vertically depending on the size and flow requirements of the customer. Let's talk a little bit more about the expansion process. The expansion process, as I mentioned before, establishes the contact between the tube and the fin to conduct the heat. We use the term interference to define the value between the developed expanded tube OD and the original fin collar ID measurement. This interference, what we call interference, must be held to a minimum value to account for the changes of thermal properties of dissimilar materials such as copper and aluminum. The industry standard value that we use for this is 4/1000ths of an inch. Now, when we consider a mechanical type expansion process where we are using tooling and materials that have a tolerance buildup, this means that there is a case where the minimum developed interference may be as low as 0.5 of an inch and the max may be as high as 7.5. While this variability may not significantly affect the heat transfer properties of the coil, it will, however, in a standard compression expansion process, affect the accuracy of the final coil length, and it will vary like the raw material will if uncontrolled. We will discuss later in this presentation about how new technology of expansion has eliminated this concern. Now that the coils are expanded, the next step in the process is brazing. Brazing is the process by which the open end of the tubes are closed and thus create the circuits for fluid movement within the coil. Here also auxiliary items such as capillary tubes and manifold headers may be added. Return bends are installed by pressing them into the formed ends of the tubes from the expansion process. This can be done manually or with an automated machine. If the coils are to be processed using an auto brazing line, the return bends have the brazing ring pre-installed and contains the material required for the brazing process. Auto brazing lines are used for large volume production. Here the coil translates through a furnace system to heat the tube ends and return bends. Hand brazing is typically used for lower volume or specialized coils or attachments. Now that we have the coils brazed, some coils go through an additional step to form them into particular shapes to fit into housings. Coil forming machines provide the means to shape the coils to fit the housings for which they will be installed. Outdoor condenser coils are typically formed into L, U, or D shapes by bending the coil perpendicular to the tubing. Also, coils can be formed by bending the coil parallel to the tubing. These are typically seen in many split evaporator coils. See those down here at the bottom. Okay, now that we have described the coil manufacturing process in general terms, let's briefly discuss some historical trends we have seen in coil designs and machinery requirements. When witnessed over a span of decades, coil design has evolved to meet many challenges and requirements. While not totally inclusive to all coil products, tubing diameters have generally been reduced over the decades, and it does give an idea of how designs have progressed. The transition to smaller tubing and denser patterns has been a result of many factors, including changing refrigerant types and pressure, and the need to provide higher efficiency systems. Back in the 60s, a typical range of tubing used in coils may have ranged from 5/8 to 3/8 of an inch. As requirements change with coil design, 7mm tubing and 5mm tubing have been introduced. We have started to see interest in tubes smaller than 5mm as well, and predict that by the end of the next decade, the trend will continue, and we may be designing and building coils with 3mm tubing as well. Another driving factor in some of the trends that have occurred is a reduction of costs of material associated with things like tubing and fin stock. There has been, for like a 3/8 tube, we have seen reductions in tubing walls from 20 thousandths to 18 thousandths. Fin thickness reductions have lowered from 5 thousandths to under 4 thousandths of an inch. While that might not sound like a lot, but when you consider the volume of coils produced and the amount of raw material needed, that reduction in raw material prices is significant. Another area that we have seen many changes in is the use of alternate fin alloys. Stronger fin alloys have been introduced as a means to reduce fin damage due to handling during manufacturing and in the field. This has resulted in the need for higher tonnage presses. So now that we have covered the general coil manufacturing process and how trends have developed the need or want to use coils with smaller tubing, let's discuss the manufacturing considerations and solutions related to small diameter tubing coils. It's good to note here that manufacturing of small diameter tubing coils is not necessarily more difficult, but just different than larger tubing coils. As is true with most other products that evolve over time, machinery developed in previous eras may not be well suited for today's new requirements. That's okay. We as machinery builders and coil manufacturers have understood the challenges required, and we have innovated to bring forth new technology and improve processes. We know that we have solutions to the manufacturing considerations, but for the sake of full disclosure and information, let's discuss some of those issues. The three primary areas of coil manufacturing that we have had to address and provide solutions for are fin production, lacing, and expansion. In general, 5mm coil patterns are more dense than 3/8, given the same physical space. With fin production, this is not necessarily a problem. However, the reduction in fin hole size is a consideration. Small tube diameters require that the fin stacking units have smaller rods due to the smaller fin hole. This results in a much more flimsy rod that is susceptible to vibration and deformation. As I mentioned before, 5mm coils contain more tubes than 3/8 in a given space. What does this mean? Well, it could mean more labor, and in fact it does. That means more tubes in the same space, means more hairpins, means more lacing. Okay? This, however, can be easily absorbed as raw materials savings are significant. For instance, the weight of a 5mm copper hairpin is roughly 1/3 the weight of a 3/8 hairpin. Even with an increased amount of hairpins for the coil assembly, the overall reduction in material of the copper is about 50%. Also, when you consider a reduced refrigerant requirement, this is also significant. Because tube diameters are smaller, the tubes are more susceptible to damage during the lacing process. As an operator twists, bends, and wiggles the tube into a fin pack, the tubes will be easier to deform. You can see this on the picture on the screen. This may result in more scrap hairpins. Also, with long coil construction, the hairpins are longer, And due to the length of hairpin that an operator would have behind them during the lacing operation, the hairpin may experience additional damage due to bending. For the expansion process, we have two considerations that new technology and processes have solved. The first consideration is understanding the behavior of small diameter tubes and why mechanically expanding them may represent opportunities. As the tube size has decreased, the normal tools that we use, bullets and expander rods, get smaller and become weaker. However, as the tube gets smaller, its hoop strength increases, increasing the force required to push the bullet through the tube. In addition, as tube diameter decreases, the tube has less column strength to resist buckling of the tube. Small imperfections in the tube strength will result in coil buckling. This scenario has required machinery builders to innovate to solve this problem, and we have. Another manufacturing consideration for producing smaller diameter tube coils is forming the bell and flare. As the tube diameter decreases, the material elongation needed to make the flare is increased as shown in the diagram. The maximum elongation of the tube material is a limiting factor. For copper, typically 40 to 50%. When maximum material elongation is exceeded, splits occur in the tube flare, and in some cases transfers down through the bell form. Also, as diameters decrease, the variation of the tube stick out, the length of the tube above the end sheet, in this process has greater impact on the ability to produce a good flare. The diagram shows the variation in material elongation caused by a 1 millimeter tube stick out variation. As you can see on the left diagram, the elongation of a 5 millimeter tube for a standard flare geometry is already at 52%. When you take into account a 1 millimeter increased stick out length, that brings a 5 millimeter tube elongation to 75%, which would result in many more split flares and bells. Here we see the effects of variable length tubing in the real world. While this consideration is valid for all tubing sizes, smaller diameter tubing is more susceptible to variability based on the relationship between the height of the flare and the diameter of the flare. This is solved by manually reworking the tube ends and provide proper flares. However, new technology has been developed to eliminate this from all types of coils during the expansion process. As we discussed during the presentation of the considerations, we as machinery builders and coil manufacturers have invested great effort to provide the innovations necessary to make moving to small diameter seamless. To improve fin stacking, a new heavy-duty stacking unit has been developed to stiffen its structure to prevent unwanted flexing during operation of the press. This will keep the stacking rods in better alignment with the fins as they are being produced. New stacker rod tip designs also allow for easier piloting of the fin as the fins are dropped from the suction unit onto the stacking unit. This allows the fin to orient itself properly, thus improving the stacking process. In the lacing operation, many considerations can be overcome by operator training and adjusting how to handle smaller diameter hairpins. This includes using more care in aligning the tubes to the fin and adjusting the amount of physical force an operator may exert on the tube during the lacing process. Also, providing better hairpins will result in better success during lacing. Providing legs that are more parallel with each other will improve the insertion of the tubes into the fin pad. Here we see an example of what we would consider a substandard hairpin with the legs a little bit bowed out, and here we see a good, nice parallel set of legs for this hairpin. Ultimately, an automated solution may be the most desirable in this process. A tube insertion machine will allow the tubes to be properly supported and inserted and take out the human factor. Also, particularly with long coils, it may be beneficial to use automation to transport the finished laced coils to the expander to prevent unwanted damage to the coil by handling. There are a couple solutions available for the expansion process. The first one I'd like to talk about is limited shrink tension expansion, and it's an adaptation of a traditional tension expansion process. With this process, the coil is held from the top with a series of clamps around the tube ends. And then also at the bottom of the coil is a clamp that holds the hairpin down at the bottom of the machine. As the bullets enter the tubes at the top of the coil, the expansion forces place the tubes in tension. Because the tube is in tension while expanding, the shrinkage or the change in length of the coil is less than a conventional mechanical compression expander, typically between 0 and 1%. The advantage here is that this process puts the tubing in tension as it is expanding. Another solution for our considerations of expansion is what we have called the pressure expansion process. Here, we use a fluid, either air, in some cases water. For this discussion, we will talk about using high pressure air, and we will inject that into the inside of the tubing. And as we do that, it expands the tubing from the inside. The pressure inside the tube causes it to expand also puts the tube in tension. This tension prevents the tube from shrinking in length and provides a 0% shrink rate. Both of these solutions provide the main advantage versus conventional expansion in that the tube will not buckle. A solution to the consideration of inconsistent bell and flares of small diameter tubing is a two-stage bell and flare process. This process incorporates a two-stage bell and flare method to eliminate related rework caused by an improperly formed bell and flare. Here we see the first stage that creates just a bell portion of the form, and then the second stage would prepare the flare portion of the form. The flare tool provides the proper flare diameter even when the tubes stick out from the end plate of the coil varies. As you can see from the picture, even though the stick outs are various lengths from the end plate, the diameter of the flare is consistent. So what are the effects of using small diameter tubes? So with higher hoop strength, it allows for the tubing and coils to withstand higher operating pressures. This has resulted in the need for alternate expansion methods to be necessary, and we as machinery builders have supplied that. Also, as a change to smaller diameter tubes, it likely occurs with a reduced wall thickness. So that means a material consumption reduction and cost savings for the manufacturers. This reduced column strength also requires controlled lacing and alternate expansion methods, which have been discussed previously. Greater fin complexity in both the design and density is capable here with the 5 millimeter or smaller tubing. This has allowed us to provide a solution for this process by improving also the stacking process. And for the next portion here and to wrap up, I'll pass this back over to Daniel.
Okay, thank you, Rocky. Thank you, Yoram, for this very comprehensive and informative presentation. So here I am wrapping up this webinar, and just to recap what I mentioned in the beginning and to highlight the importance of manufacturing solutions and finding solutions for the challenges for small diameter tube heat exchangers that people like Rocky at Burr Oak Tool work really hard for. From a market context, back in 2011, we had 134 million air conditioning units made. And this is not counting refrigeration nor any other air-to-refrigerant heat exchangers. Each air conditioning unit has obviously 2 heat exchangers, which means 268 million heat exchangers, which corresponds to 8 heat exchangers being produced every second. Out of these, 25% were small diameter copper tube heat exchangers. So we're talking about 2 heat exchangers per second being produced back in 2011, and this number only tends to increase. And as the technology develops and increases, we hope that within the next decade we'll be able to start seeing tube diameters of 4 or even 3 millimeters as proposed in the historical trend presented earlier on. So before we move on to the Q&A session, just a reminder of next month's webinar, the webinar number 3, which is the effective design of small diameter copper tube feed heat exchangers, where we're going to use our in-house software Coil Designer to show how, well, give a simple demo on how to model and simulate heat exchangers, and specifically how to apply that to small diameter tube heat exchangers, and present some real cases where we use Coil Designer to design these heat exchangers and validate it with experimental data. So please go ahead, go on the link and register for webinar number 3. And now I would like to thank you all for your attention. We have another 10-15 minutes where we can now answer your questions. So please type in the chat box, and I will read the questions aloud, and Rocky or Yoram can address them to you. Looks like Rocky did a very good job. Nobody has any questions?
Perfect.
Okay, so we got one here. Okay, what is the smallest tube you have expanded in production?
Well, the smallest one that we do is 5 millimeter. However, there have been initiatives in the past, even 15 years ago, where 4 millimeter was a product that a customer had attempted to use. We are currently concepting smaller diameter tubes, and we have assembled 3 millimeter tubing coils that we use our pressure expander for. But as far as production, 5 millimeter really is where we're at as far as a minimum size at the moment. I think there's, coil design requirements and a lot of more math than I can probably come up with before, we get into the 4 and 3 millimeter when the coil designers will really grab hold of that. But we're hopeful, and we think that's where things are headed.
Okay, we got another one here. What is the maximum length between tube and sheet that can be expanded?
Well, I don't know that there's a maximum. I think the difficulties or challenges are a little bit different. A shorter length coil, it's 5 millimeter, you have quite good success rate, I think, capable to you. As the coil length gets longer, you have to have the shrinkless expander or the pressure expander really to have really good success. With pressure expander, I don't see really a limitation on the length, but typical expanders that we do traditionally don't get longer than, I guess it would be 3 meters. That's primarily because like an outdoor condenser unit has somewhat of a maximum length that's really developed. Commercial type coils, they will get longer than that, but I think it's it's not a factor of how long, because if you can build it to do 10-foot long coils, you can probably build it to do 14 or 16 just with additional mechanism or length in the machine. So it might have been a long answer, but the short answer is we do about 3 meters, but it's probably capable of going longer than that.
Okay, we have a couple more here. One, with smaller diameter tubes, you also need more circuits. How does cost of header impact the design choice?
I don't know that I'm the right person to answer that. I'm just a machinery builder, so I don't know exactly about the coil design. That may be, Daniel, is that something that you guys have addressed or will address in the future webinar?
We'll address the design perspective of it. I don't think I can tell how much it impacts the cost directly, but we can include that for a webinar number 3 and address there then. So there's another one. Is the cost per length of small diameter tubes considerably higher than 3/8 inch tubes, eliminating some of the cost savings compared to material savings?
As far as the raw material costs, I don't know. Yoram maybe has some insight into the difference in price on the actual copper tubing itself. As I don't know if that's what I understand the question to be, like, given all things equal, does the cost of a 3/8 coiled tubing cost more or less than 5mm coiled tubing, regardless of what the amount of weight of the coil is?
Yeah, the question is, Rocky, the question relates to the tube cost or the coil cost. I'm not sure. 5mm tubes are simply a continuation of a drawdown process of a larger tube. That process is on the fly, and an additional stage does not make the tube more expensive. As I mentioned, you get a considerable amount of tubing from the same billet when you start. Also, the material thickness on a 5mm tube is lower than a 3/8 by maybe a small margin. So I would say the answer is no, it is not more expensive in any manner that is of importance. Now, when it comes to a coil, it relates to the coil. That is a little more complex because the coil is more efficient and it can be made a little smaller. So there are cost savings there.
Okay, so there are a few more here. One, would you still use mechanical expansion for small diameter tubes?
Well, I think you're gonna run into a physical limitation already at 5mm when you consider trying to put a steel ball and a rod down through the expanded or unexpanded ID of the tubing. It's a significant change from 3/8 coil construction. Like a 3/8 coil construction, you're using a 5/16 diameter expander rod. Well, now when you consider a 5mm tubing coil, that size gets down to let's see, 3.5mm, I think. Roughly 140 thousandths is what we use. So when you consider trying to go smaller than that, it's be like pushing on a piece of, uncooked spaghetti. It's pretty small. So that's why, we have seen the growth of this product and an avenue for us to provide good solutions for the industry by eliminating the rods and the bullets from the scenario.
There are a couple more following up on that. One, would then the recommended interference change?
I think technically you could, but as I mentioned in the discussion about the tolerance seen on a mechanical type expansion, If you try to reduce it too small as far as what you're going to use as a nominal interference, if you have a batch of tubing, maybe that's a little bit undersized as far as the wall thickness, you may come into a situation where the fin collar and the tubing aren't making that intimate contact. So could it be reduced? Slightly, but 4 thousandths is still not a large value. So if you reduce it down a couple thousandths, maybe you'd be okay with that. But I think it's a factor of the raw material and the tooling that you use in the mechanical system. The pressure expansion, I don't see that as a problem because we don't necessarily care about the tolerance of the tubing wall, or we obviously don't have a bullet, so you're just basically blowing up a balloon from the inside. So in this case, just coming up with the ideal heat transfer interference fit, yes, you may be allowed to come down in interference fit on the smaller diameter tubes. I believe OTS has, I don't know if that's something you guys are discussing in the third webinar as far as the heat transfer capabilities based on that. I don't know if that was part of the context. So
still working on it. It's good. Well, at least we're having a feedback here. We can potentially address all these the next webinar. And there's a last follow-up question from the same person on that topic. Are there any publications regarding optimization of the interference? Do you know?
Yes. We have presented through our innovations manager, Roger Tetzloff here. I believe we have, I apologize, I don't have it with me right now, but there is a white paper, I believe, that documents some of that minimum interference, and then how much more beyond that is really necessary for the heat transfer to be a good situation. So I will be able
to, if people contact you, would you be able to provide that?
Yes, and I will see what I can dig up, and then I will probably pass it along to you as well, Daniel.
All right, thank you. So please follow up with Rocky further on later after the webinar if you need more information on that. Now moving on to another question. Well, if mechanical expansion is continued with, would you redesign the bullet expander in terms of shape, size? Well, size would obviously change, but would you redesign the bullet expander?
Like the design of the machine? I don't know if that's what the focus of the question is. The design of the machine, possibly with the longer 5mm or smaller coils, it's probably a better style of design a machine for it to be in a horizontal orientation and stay in that orientation. Typically when we do long coils, our machines are still vertically oriented, and the coil is brought in horizontally and then lifted up to a vertical position. And this is primarily a space savings feature. However, with such maybe some long and slender coils, it may be of a benefit not to handle or move that coil as often, in that if you can provide a horizontally oriented machine that the coil comes onto a loading station and then passes through horizontally to the expanding station and then off to an unloading station, that's going to be a better flow path as far as the coil and the machine design.
Okay, let's go over a couple more here. This one I think it's more for Yoram. What's the impact of the tube enhancement on the manufacturing cost as the tube diameter becomes smaller?
For 5mm, as you saw in the slides, the enhancements are really part of the process. It's a matter if you're talking about the roll and weld, it's a matter of embossing the inside or not. and the casting process. There's a floating mandrel inside, so it's in line with the manufacturing of the tube, and there is hardly any price difference in the tubing if it's grooved or not. Now, grooving tubes below 4 millimeter is actually a question of a design. It's under investigation. I think 4 millimeter is kind of the borderline for the effectiveness. Maybe 3 millimeter does not require much enhancing because the distance from the center of the tube to the wall is very small to begin with. And there are some studies that looking into it. So for the cost, there's hardly any difference. If it's necessary below 4, this is still under investigation.
Does the pressure expansion work with welded tubes?
Yes, it does.
Yes, the welded tubes are annealed before they're packed, so the stresses are removed, and as Rocky can confirm, it does.
Yes, it does.
Okay. And what is the typical wall thickness for a 5 millimeter tube, and what would be the expected wall thickness for a 3 millimeter tube?
Yoram, do you want to take this? I think I have about 15 thousandths wall, I think, for 5 millimeter, but
it's about 0.23 millimeters. Let's see if that's right. It depends if you count the grooves or not. So there is the basic wall, and then there are the grooves. You can see it online accurately for the tube that you're looking into, because there are different types of tubes. You can actually get tubes with different wall thicknesses. 0.2 is pretty common, and you can go online either. As an example, any tube manufacturer will have its product online, and you can select what you need.
Okay, so it's about 4 or 5% of the tube OD.
Yeah, give me a second. I'll give you an exact answer.
Okay, while you're doing that, just going back to the mechanical expansion, Rocky, I guess the question was not, it was about the design of the bullet. If the bullet would change its shape or anything else if we reduce the tube diameter, not the process itself, but the bullet itself.
okay. The only thing that we have done in a 5 millimeter situation is, because typical construction of attaching the bullet to the end of the rod is to use a separate screw to from the bottom of the assembly, screw the bullet to the end of the expander rod. Given that the diameter of the bullet is so small, you can try to go with smaller screws yet, but what we have done in that situation is we have built the threads into the bullet, so it's a shank style bullet. So that type of change in construction is usually warranted. As far as the shape and style of the bullet, well, when you get rid of a bullet screw at the front or the nose end of the bullet, you can go with a much more gentle taper, 5 or 10 degrees, as opposed to maybe a 15-degree nose on the shape of the expander bullet.
Okay, if you want the numbers on the wall of a 5 millimeter tube, one manufacturer, and we're not going to name because there are many out there, the base wall is 0.23 millimeters, and the inner enhancements are 0.15 millimeter tall, and there are variations of it. Some manufacturers I have seen that have a base of 0.2 millimeter, and the inner grooves are about the same, 0.15. That's the most common.
Would you expect it to remain kind of in that range if we move down to 3mm?
You could manufacture these tubes with the thinner walls, but the handling will become more of an issue, as we have seen. So it's a matter of handling, and of course from a pressure point of view, you could go thinner on the wall. So if your heat exchanger is not very long, you could go thinner on the tubes and save more metal.
Right. Okay, very good. I think we wrapped up all the questions. If anyone has any additional questions, you can contact us. You have our contact information here on this slide. And just a reminder, this presentation was recorded and will be made available to you tomorrow, along with a copy of the PDF and a feedback survey that we, again, highly encourage you to fill it out, especially for those who are interested in receiving a simple heat exchanger. So with this, I will conclude webinar 2, and I hope to see you all on webinar 3. Thank you very much, and have a wonderful afternoon.
Thank you all.